Okay, here we go with topic 9.5, the Doppler effect. I should have finished eating my lunch before I started. I'm sure many of you have heard of the Doppler effect before, but you probably haven't done anything on it numerically. When a police car is coming towards you, or an ambulance, you can hear the siren coming, making noise. As it moves away from you, the sound of it changes, the frequency of it changes. It sounds like it's going a lower note. So as it comes towards you, new, 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 then it goes back, new, 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 so a lower note. Why? Because the waves get squashed up or spread out. If I filled the classroom with water, not the whole classroom, but just half a metre deep or even 5 centimetres deep, and was dipping a ruler into the water, then circular waves would spread out just like this. Okay? And someone sitting over there, they could watch the waves coming towards them, they could measure the wavelength, they could measure the frequency, they could measure the speed, and they would get exactly the same answer as I was getting as I sent them. The frequency that they measured would be the same as the frequency they were generated at, and the same with the wavelength and the same with the speed. If I move towards that person while I'm generating the waves, then we get a separate situation. Let's go through this first. So here's the source. Whether they are sound waves or water waves or light waves, the same thing applies. The waves are heading out, it's a constant wavelength here, constant wavelength here. The circles may not be exactly concentric, but concentric, same centre. But hopefully that's not too bad. The observer sees or hears F waves pass him or her each second. They measure the speed as v and the wavelength as lambda. So the wavelength is the same as lambda naught. Lambda naught, what it's being generated at. The speed is the same as the speed that the observer is, that the source is sending them at, and F is the same as F naught. However, if the source or observer is moving, in this case the source is moving. Alright, so it's me moving towards the observer and dipping those. So the centre of this circle is over here somewhere, the centre of this one is here somewhere, the centre of this one is here somewhere, the centre of that one is there, and the centre of the last one is here. So the source has been moving across like that. So we're getting a smaller wavelength here and a bigger wavelength here. Again, it's hard to draw that diagram accurately. I've left the computer back there, Brian, but there was a message that came up saying that it had been up for review, or it had been reviewed, or it's being reviewed, or something like that. Okay. So the wavelength in front has got pulled out, from what my diagram there, they look a bit different, but it should be constant, 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 and a different constant, 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 constant back here. Pretty hard to draw that diagram, haven't tried it. But clearly, the observer, if the source is moving towards them, they are measuring a smaller wavelength. What that does, we'll find out. If the observer was here, the waves would reach them, but they would be measuring then a bigger wavelength. If the source is moving towards the observer, the wavelength measured by the observer will be less than lambda naught. Lambda naught is what it's being generated at. The speed of the waves is still the same, and that's it's an important one. If I'm standing here generating the waves are travelling out to all of you at 2 metres per second or whatever it might be, depending on the depth of the water and so on. If I'm moving towards you, it's not making the waves go faster. If I'm walking towards you, it's not making the sound go faster. If I'm moving away, it's not making the sound travel more slowly to you. It is changing other aspects of it, but not the speed. We're only going to change the speed if we change the medium. If the air changes, if we're going from air into water or something like that. but there's no change in medium, so the speed is not changing. Important point. Alright? So if the wave is moving at speed c, now we often use c, that of course is the speed of light, but often we can use that as the speed of a wave. Alright? And the source is moving at speed v. So we've got two different speeds there. The speed of the wave is c, the speed of the source is v. It can be quite tricky knowing which way around things go. The frequency is f naught, the wavelength is lambda naught, v equals f lambda, or c equals f lambda, or lambda naught equals c on f naught. So you've got those links there, the relationship between the speed, the frequency and the wavelength. The wave equation, almost the most important formula in physics, after f equals ma, v equals f lambda. In 1 second the source will have moved a distance v, alright? So the source is moving at 3 meters per second, the wave is moving at 5 meters per second, for example. In 1 second, the source will have moved 3 meters, but the leading edge of the wave will have moved 5 meters. So that distance there will be 5 minus 3. If the frequency of the wave is f, that's how many waves we're getting in a second. So the number of waves emitted will be f, and the observer will measure those f waves in that distance there, and that distance there is c minus v. So the wavelength that the observer measures is lambda is equal to c on f. The wavelength is equal to, the wavelength will be that total distance over the total number of waves. The total distance is c minus v, total number of waves is f. So that's lambda dash, what the observer is going to measure. And lambda dash is equal to c on f dash, because the speed is still the same. So c equals f dash lambda dash. So f dash equals c on lambda dash, and lambda dash is this, c minus v on f. So plugging that in, we get this. Simplifying that, we get that f dash is equal to c over c minus v times f naught. So f dash is some factor, some multiple of f naught. That number might be more than 1 or less than 1. In this case, if the source is moving towards the observer, then we're going to measure a frequency higher than f naught, but if we're moving away, then it becomes greater than f naught. So I'll write out that equation again. It's really f dash equals c on c plus or minus v times f naught. That's in your data booklet or an equivalent. For example, a police car has a siren giving a note of 600 hertz. A police car is travelling towards Om. I'm not sure what Om has done wrong, but there's a police car travelling towards her at 108 kilometres per hour. Well, first of all, we need to know the speed of sound. Let's say 340 metres per second for the speed of sound. Speed of sound C is, say, hang on, no, C is the speed of light. In this case, because we've got the two speeds, we're using c as the speed of the wave through the medium. It's not changing. By me running, I can't make the sound travel any faster. I can't make light travel any faster by moving towards someone with the torch. I can change the frequency and the wavelength, but I can't change the speed. Okay, speed of sound is that. So, f dashed equals c over c minus v, 340 over 340 minus 30, so 108 kilometres per hour equals 30 metres per second, hopefully you can make that change, times f naught times 600. And we're expecting an increase in the frequency, but not a huge increase in the frequency. Yeah, so when the police car comes towards you, as it passes, the sound gets less, but not hugely less. So that's 340 over 310 times 600. I don't know what that is. That's 30. It's about 10%, pretty close to 10%, just under. I'm going to say 660, probably a bit less, 658 hertz. Again, that's just an estimate, I don't know what the right answer is. 240 over 310 is 30. So 1 and 30 over 310, so just under 10% here, something like that. Okay. And if you calculate that, you might find 656 or something like that, that's okay. Alright, so that's the frequency if the police car away, then F dash is equal to C over C plus V times F naught. And it's really hard to know, whether you're using the minus or the plus, but just what makes sense. If it's coming towards you, you're getting a higher frequency, so therefore the bottom line is smaller. If it's moving away from you, then the frequency has gone down. So now we've got that F dash equals 340, over 340 plus 30 times 600 equals 340 over 370 times 600 equals whatever that is. So just, again, about 30 over 370, a bit less than 10%. That might be 550 hertz or something like that. So it's a higher note as it comes toward, it's a lower note as it moves away. So, and just very easy to get things around the wrong way there. So just, is it making sense? If it's moving towards you, then it's a higher note. If it's moving away, then it's a lower note. If the observer, yes. Is it a plus or is it a minus? Well, just what makes sense. If the observer, if I'm moving towards the source, again I'm crossing more wavelengths, I'm getting a higher frequency. And so I'm going to be using the plus in that situation to make it a higher frequency. Okay, so where do we use this? So first of all, the Doppler effect it'll only be noticeable if the speed, the relative speed of movement. So first of all, if I'm in my car chasing a police car, or maybe more likely the police car is chasing me, and we are both moving at the same speed, then there's no difference in frequency because there's no relative movement. All right? Whether I'm moving towards the police car is moving towards me, or we're moving away from each other, then we'll have the change in frequency, there'll be a change in wavelength, there'll be no change in measured speed of that wave. But if we're both going at the same speed, then there's no change in frequency. All right. If I'm talking in class and walking around, which of course I'm doing all the time, then I'm speaking at 300, 400, 500 hertz, a mixture of all that. the speed of sound is roughly 340 metres per second. If I'm moving towards you or away from you at 1 or 2 metres per second, 1 or 2 out of 330, 340, you know, that's 1/3%. You're not going to hear any difference. Okay? You'll hear it louder as I'm coming towards you, you'll hear it softer as I'm moving away, but you're not going to really pick up any change in frequency. There is, but it will be so small that you wouldn't pick it up. Similarly with light. You know, light's travelling at 3 × 10⁸ metres per second. If I'm moving a torch towards or away from you, or the police car coming towards us at 30 metres per second, do the coloured lights look different? No. Only because they are different, but so little. It's 30 out of 300 million, 3 × 10⁸. So that's 1 in 10 million. Well, you can't pick up, you can't see that change in frequency wavelength of light. But if something is travelling close to the speed of light, then you would notice, or not even close to, at some reasonable fraction, even 1% of the speed of light. And so with stars, we do get that change, and so we're able to pick up that spectra from stars. We may well cover this in the astrophysics option as well. But spectra from stars can be shifted towards the red end or the blue end of the spectrum. We talk about the redshift of stars. That's because they're moving away from us, and so we end up measuring a longer wavelength or a lower frequency. Only just. So redshift doesn't mean that things look red, it just means that they get shifted a little bit towards the red end of the spectrum. So something that was red still looks red, something that's blue just looks a bit greeny blue, it's just been shifted a little bit along the spectrum. We use it with radar for cars. So when they, the police shine the radar gun at you, the pulse that goes out and the pulse that come back are at slightly different frequencies because it's come off the moving car, and the difference between those can be used to calculate the speed. They can use it to measure the speed of blood flow in your veins, so anything that's moving there. So there are certainly uses of it, but the Doppler effect will only be noticeable if the speed of the source or observer is reasonable. And really we're only talking about two things, that we're talking about the speed of sound, 340, and so with aeroplanes they can travel not only close to the speed of sound but beyond the speed of sound. When they travel at the speed of sound, all those wave fronts in front of them are all together, and that gives you a real shock wave, and as you pass the sound barrier. So, as far as I'm aware, there are no commercial planes that fly above the speed of sound. There was, but that was that became too difficult, and was sort of the Concorde was shaking bits up and so on, and there was of course a crash of the Concorde. Air Force jets travel faster than the speed of sound. They might travel at Mach, M-A-C-H, Mach or Mach 2 or Mach 3, I'm not sure what the fastest is, maybe 4-5, Mach 5, Mach 6, so they travel very fast, faster than the speed of sound. But they're not going to travel close to the speed of sound because all that sound and vibration is right with them and shaking them up. Okay, so sound, 340 metres per second, light, or other EM waves, 3 × 10⁸ metres per second. So of course, radar, microwaves, infrared are travelling at 3 × 10⁸ metres per second, and so you would have to have very sensitive equipment to be able to pick up that small difference. And So just while I don't speed because they don't pick up me doing anything wrong. And sometimes. Okay, I reckon that's Doppler effect. Okay, that's the end of topic 9. Something I've already spoken to about topic 9, but that's, you know, really, in term 2, we've got topics 9, 10, 11 and 12 to do. I don't know when we'll get back to school, hopefully early in term 2. I'll put up topic 10 in 2 weeks' time. Alright, so this has given you all of topic 9, lots of questions from the book to get through, 9.1 and 9.2. Okay, by all means send me an email if you've got any questions with it. Bye.